This is a video to address a student question on section 5.1, number 9. We're dealing with eigenvalues in this section, and the problem says, let lambda be an eigenvalue of an invertible matrix A. So we know that lambda is an eigenvalue and matrix A is invertible. Show that lambda to the negative 1 is an eigenvalue of A inverse. Hint, suppose a non-zero x satisfies ax equals lambda x. Now their hint comes directly from the definition of an eigenvalue. Since we know that lambda is an eigenvalue, we know that by definition for some matrix A, it satisfies ax equals lambda x. And the other thing to note is that lambda is a scalar. So when we talk about lambda to the negative 1 for a scalar, that's just 1 over the scalar. So we're not exactly dealing with an inverse with lambda, we're dealing with 1 over lambda when we talk about lambda to the negative 1. So those are just a couple things to note before you start the problem. Now the problem says, note that A inverse exists, because we're told that in the problem, the matrix is invertible. In order for lambda to the negative 1 to be an eigenvalue of A inverse, there must exist a non-zero x such that, and the student already selected, A inverse x equals lambda to the negative 1x. Now that is just definition of an eigenvalue. If lambda to the negative 1 is an eigenvalue of A inverse, then A inverse times some non-zero vector x has to equal lambda to the negative 1 times that same non-zero vector x. Now suppose a non-zero x satisfies ax equals lambda x. Again, that's definition of lambda being an eigenvalue of A. What is the first operation that should be performed on ax equals lambda x so that an equation similar to the one in the previous step can be obtained? So when they talk about an equation similar to the one in the previous step, they're talking about this equation A inverse x equals lambda to the negative 1x. Okay, so a couple things to note. One is that we're starting out with the ax equals lambda x. That's what they tell us. If we want to get something similar to above, then what we want to do is we're going to multiply both sides of ax equals lambda x by A inverse. Now, right or left multiply does make a difference because remember the matrix multiplication does not commute. So I would want to multiply on the left by A inverse. And so I'm going to select left multiply both sides by A inverse. And so what I get, if I do that, I get A inverse ax equals A inverse lambda x. And we know that this is the identity. A inverse times A is the identity. So this becomes x equals A inverse lambda x. So that's what I'm going to put in the simplified answer box here. X equals A inverse lambda x. Okay, so notice we're not exactly where we want to be because we're trying to get to this right here, and we're right here. So we want to get to A inverse x equals lambda inverse x. And right now, we're at x equals A inverse lambda x. So we have a little ways to go first. Now the next question says, why does this show that lambda inverse is defined? Select the correct choice, and if necessary, fill in the answer box to complete your choice. So what I'm going to do is I'm going to look at what we know. What we know from the problem statement, we know x is an eigenvector, so that would mean that x is non-zero. And we know that A is invertible. Those two things were told to us in the problem statement. Now in the other choices, in choice A, it says A inverse and x are commutable. No, that would not work because the size wouldn't match up if you commuted for multiplying the two. And C says, since the product lambda to the negative 1x must be defined and non-zero, lambda to the negative 1 must exist and be non-zero. Now, the product being defined, we're not told that, and so we're not going to select that option. We're going to select the option B, because by definition, x is non-zero since it's an eigenvector, and A is invertible. We were told that. So what that means is that the previous equation cannot be satisfied if lambda equals 0. Because x is non-zero up here, and so lambda has to be non-zero as well. Okay, last question. How does this show that lambda inverse is an eigenvalue of A inverse? Select the correct choice and fill in the answer to complete. So let's think about where we're trying to get to. Let's scroll up. We're trying to get to something like this. A inverse x equals lambda inverse, or I'm sorry, lambda to the negative 1 x. So down here, that is going to be this option right here. Lambda to the negative 1x equals A inverse x. So what we have to do is figure out what to multiply both sides of the equation by, multiplied by something, and then simplify it to get what we want it to be. All right. So we're starting with this equation here. X equals A inverse lambda x. So if I have x equals A inverse lambda x, and I'm trying to get to lambda inverse x equals A inverse x, I want to multiply both sides by lambda to the negative 1. And I know I keep slipping up and calling it lambda inverse, but since lambda is a scalar, it's actually lambda to the negative 1. So lambda to the negative 1 x equals lambda to the negative 1 times A inverse lambda x. Now, one thing we know is we know that lambda to the negative 1 and lambda are scalars. That means real numbers in this case. And so I can actually move the lambda to the negative 1 to the right side of A inverse. And so I can actually rewrite this as lambda inverse x equals A inverse times lambda to the negative 1 times lambda times x. Now, the lambda to the negative 1 times lambda, that's really the same as saying 1 over lambda times lambda, which is a 1. And so that's going to leave me with my lambda to the negative 1x let me write that a little better. Lambda to the negative 1 times x equals A inverse times x. So by definition, that is showing that lambda to the negative 1 is an eigenvalue of A inverse, because that's definition of eigenvalue.